In the last video, we saw that in all cases of spherical symmetry, assuming we use a spherical Gaussian surface, integral E dot dA ends up evaluating as 4 pi r squared E. And we use this to find the electric field of both a point charge and a uniformly charged sphere. Our goal now is to investigate cases of non-uniform charge density. That is, we have a density which is dependent on position. To utilize our spherical symmetry, we're specifically going to say that our density is a function of radius, right? So if we had a density which depended on, say, our x coordinate, as opposed to our radius, we would then violate spherical symmetry and could not use Gauss's law in the same way. So we suppose that we have this density rho of r, and of course the definition of rho of r is that it gives us charge per volume. And so to find our charge enclosed, we can say, well, dq is equal to rho of r dv, and then go ahead and integrate both sides. So how are we actually going to carry through this integration? Let's consider breaking up our sphere into spherical shells of infinitesimal thickness dr. I'll argue that the surface area of such a shell, if it is at radius lowercase r, let's maybe draw that a bit lower. So if it's at radius lowercase r, then its surface area would be 4 pi r squared. And since its thickness is dr and is infinitesimally thick, we can approximate that dv, our infinitesimal volume, is 4 pi r squared dr. And so I can now rewrite that integral dq is equal to integral rho of r times 4 pi r squared dr. And now we can make things concrete. And suppose we're given a particular density. For example, I could say rho of r is equal to alpha r. Then I can say that my charge enclosed up to as a function of r less than big R is equal to integral 0 to little r alpha r times 4 pi r squared dr. And then going ahead and integrating that, we can pull out the 4 pi alpha. We get integral 0 to r cubed dr. And this leaves us with 4 pi alpha r to the fourth over 4. So now putting this into Gauss's law, remember left-hand side of Gauss's law still has 4 pi r squared E is equal to now 1 over epsilon naught times pi alpha r to the fourth. And so we get E equals pi's cancel alpha r squared over 4 epsilon naught. Now, suppose we're asked a related question, namely, suppose we're asked, what is the value of alpha? So find alpha. We've already discussed this in the context of direct integration for electric fields before we began Gauss's law. This is yet another case of charge normalization. And so suppose we know that the total charge of our sphere is q, and that our total radius of the charge distribution is r, then we know that integral dq equals capital Q if we integrate our density from 0 up to capital R. So in this case, if we just use our density alpha r again, we have alpha r times 4 pi r squared dr, which evaluates to 4 pi alpha r to the fourth, evaluated from 0 to r. And this ultimately gives us, oops, dropped a divided by 4 right there. And so ultimately this gives us pi alpha r to the fourth. And so we can now solve for alpha, namely that alpha is equal to q over pi r to the fourth.